All right. Good afternoon. Thank you all for coming to our RAL M Cubes joint seminar. And welcome to those here in person and the many people online as well. So welcome here, Dr. Andrew Winters, who is an assistant professor in the Department of Atmospheric and Oceanic Sciences at the University of Colorado here in Boulder. And he's been leading the Synoptic Meteorology Research Group since August 2019. And his research group does a lot of broad topics of research, and including some work with people here at NCAR. A lot of his work is in the realm of dynamics, variability, predictability of synoptic scale environments that give rise to high impact events. And his work spans a variety of topics, including the topic today of polar subtropical jet superpositions, North Pacific jet variability and its connection to extreme temperature and precipitation, lee cyclogenesis here along the Front Range, near freezing precipitation, including some field campaigns of launching balloons in horrible conditions in Canada, and atmospheric rivers. And is already in his illustrious career co-authored over 35 publications. He has a really vibrant research group at CU Boulder of graduate students and postdocs. Going back in time, he's earned his PhD working with Jonathan Martin at the University of Wisconsin in Madison. So we overlapped quite a bit while I was there, but we never actually met up, so it was funny that I actually met him when I visited at Albany where he was doing his postdoc a few years later. So he did his postdoc at Albany prior to coming to CU Boulder, working with both Daniel Kaiser and Lance Bossart. So a lot of great people in his lineage. So anyway, I'll stop talking and hand it over to you. Everyone welcome Dr. Andrew Winters. Awesome.
Thanks for that great introduction, Chris. Yeah, it's a pleasure to be here. Really excited to share a little bit about a topic that I started studying about 10 or so years ago when I was a grad student at the University of Wisconsin. That work has since been carried on by a couple of graduate students, namely Clary Ryer and Eleanor Salm within our research group here at CU Boulder. And all of this is culminating, as I'll mention at the end of this talk, in our opportunity to really study these features observationally in great detail for the first time. And so I'll talk a little bit towards the end about some NASA field work that our group has been involved with to better understand these jet superposition features. And so just to kind of conceptualize this idea of jet superposition, I always like to think about the merger of two separate tributaries is identical or a corollary to what we see in the atmosphere, where we have a separate polar and subtropical jet stream that can merge into a unified jet structure. And just like you can have with these merging tributaries that can lead to, let's say, greater stream flow within the downstream environment in the atmosphere, when you have the merger of these two separate rivers of air, you can end up typically with a lot stronger wind speeds at upper levels and a greater capability to produce high impact weather in association with that synoptic dynamic environment. And so when I'm talking about a jet superposition, I want you to think of this conceptually as the merger of two separately rapidly moving rivers of air, these being the polar and the subtropical jet streams. And we can view this process here from a hemispheric map of tropopause pressure. This was a study that was done just based purely off of observational data assimilated by Defont and Taba in 1957. And this is for a single snapshot of tropopause pressure in early January of 1956. Right at the center, you have the North Pole. If I can get my cursor here super quick. Yeah, so you have North Pole at the center. To help orient you, Boulder is here in the green dot. And then these individual shaded regions are highlighting the height or the altitude of the tropical tropopause farther equatorward away from the center, the intermediate subtropical tropopause, and then the lower polar tropopause that's located in the vicinity of the North Pole. The polar and the subtropical jets tend to reside in these regions where you have strong gradients in tropopause pressure, denoting a spot where you have a rapid drop in the tropopause height. That's going to be where those wind speed maxima are nestled. And you'll notice when You look across the hemisphere here that while each jet tends to occupy its own climatological latitude band, there's pretty substantial meanders in the position of each jet. Here across the North Atlantic, you see a pretty far equatorward extrusion of the polar tropopause, and then you'll also notice some locations where these two separate gradient regions merge, and that's going to be where we identify a jet superposition. But if we take a look at what this typical structure looks like through separate polar and subtropical jets, you might see this conceptual type cross-section here, where you have the pole on the left and the equator on the right. And in a typical type of scenario, you would see this two-step tropopause structure with each jet nestled within one of those tropopause break regions. When we have a superposition like we have here over the North Atlantic, where you see these two gradient regions merge into a single area, instead of having that two-step tropopause structure, you have a single drop in the tropopause height from the tropical tropopause all the way down to the polar tropopause, and this is one of the hallmarks of one of these superposition events. So if we take a cross-section through one of these structures, you might see something like this, like we have here within this conceptual cross-section. And notice instead of having that two-step structure we saw originally, you have a single steep tropopause break region. This is accompanied by anomalously strong baroclinicity. You're essentially consolidating the strong baroclinicity in the lower and upper troposphere associated with each jet individually into a single narrow zone of contrast. And as a result, you end up with extremely strong upper tropospheric wind speeds in association with these features that can exceed, in some cases, upwards of 100 meters per second overall. And when you think about sort of the relationship between these structures and high impact weather events, there's been a number of studies and events that have occurred within the last 10 to 15 years that have been associated with these high impact weather events, with these jet superpositions, and they can cross-cut all different types of high impact weather, from extreme precipitation to snowstorms to severe weather. And so shown here is some of the flooding with the May 2010 Nashville flood. Ben Moore did a great study of this event, highlighting pretty extreme precipitation events across western Tennessee. At the time, this broke the record for a single or a 2-day rainfall event within the Nashville area, but it was eclipsed a year later by another event almost to the day of this May 2010 event. But some of the work I did as a grad student found that the formation of a jet superposition during this event helped to enhance the poleward moisture transport between the first and second days of the event via the ageostrophic circulation associated with the jet exit region accompanying that jet superposition. And that helped to rehabilitate the atmosphere for a second day of heavy rainfall. The October 2010 explosive cyclogenesis event, I was in Madison at the time for this one. This was an event that was associated with a squall line and severe wind reports all across the Ohio River Valley. And then all of these numbers here represent non-thunderstorm wind gusts, and at the top of the 15-story atmospheric science building in Madison, we had a 72-mile-an-hour gust just due to the strong pressure gradient associated with this low pressure system. This low pressure developed in response to a superposition that initially formed over the eastern North Pacific. It then moved across the western U.S. and induced cyclogenesis beneath its left exit region. Amanda Chastain did a great study of the April 2011 tornado outbreak. During this event, a jet superposition also occurred in conjunction with the event in response to some of the convection that was occurring during that multi-day convective outbreak that led to numbers of tornadoes all across the eastern U.S. and southeastern U.S. And then more recently, this was towards the end of February, a really intense northeast U.S. blizzard that brought upwards of 3 feet of snow to the Rhode Island area, and hurricane-strength wind gusts was also associated with a superposition that developed off the east coast of the U.S. And led to the surface cyclone developing beneath the left exit region there as well. So this hopefully gives you a flavor of the different types of extreme weather events that occur in conjunction with these superpositions, and the fact that they can occur throughout the cold season. You'll notice events here from the shoulder seasons in October and May, events in the heart of the winter, such as this one in February, And so they tend to occur over North America all across the cool season time period. So for the duration of this talk, I'll first introduce a little bit more on how we identify these superpositions and some of the work we've done to look at the impacts of these superpositions on high impact weather production. We'll then talk a little bit more about the processes that lead to their development as motivation then for discussing some of the future changes we've identified in how these jet superpositions may change in a future warmer climate. And then towards the end of the talk, I'll cover our upcoming field campaign that'll study these events in greater detail and then finish up with some brief conclusions. So if we start with looking at the identification of these events and their impacts, here I want to return to this two-step tropopause structure in this cross-section that we show here. And the basis for identifying these polar and subtropical jets is founded in the observation that each jet tends to occupy its own characteristic isentropic layer that is seasonally dependent. So the potential temperatures that bound the isentropic layer containing each jet is going to vary throughout the cool season, but typically you're going to see that subtropical jet located at warmer potential temperatures than its polar counterpart. You'll also notice that each jet is characterized in the vicinity of its wind speed maxima by a strong horizontal PV gradient, which denotes the presence of that tropopause break. And this observation also plays into the identification criteria that we're looking at. So ultimately, the foundation for this scheme is to look for areas where you have wind speed maxima that reside within a characteristic isentropic layer that we typically see for that particular jet species. And then we look for strong horizontal gradients in the PV or the potential vorticity in the vicinity of those wind speed maxima to highlight that tropopause break region. So specifically what we do is we look for that 400 to 100 hectopascal integrated wind speed to exceed 30 meters per second. This is to ensure that we have a grid column there that's characterized by a jet streak that can be conducive for inducing high impact weather via its areas of acceleration and deceleration in the entrance and exit regions. And then we also look for a strong horizontal PV gradient that exceeds a determined threshold that we come up with empirically based off the climatological distribution of the PV gradient that we typically see within those potential temperature layers. And we use that to identify whether or not we have a strong enough horizontal PV gradient that coincides within those isentropic layers. This scheme then outputs individual grid points that are characterized by a polar or a subtropical jet in terms of being co-located with those areas of strong horizontal PV gradients and wind speeds. To come up with those isentropic layers, this here shows the distribution of potential temperatures on the x-axis for each month that are associated with the maximum wind speed within each grid column within the Northern Hemisphere throughout the period of November through May 1980 to 2020. So it's basically trying to identify what typical potential temperatures do you associate with the maximum wind speed within each column, and how does that change as a function of month of the cool season using ERA5 data. And so from this particular distribution, the green shaded bars are representing what we will denote as isentropic layers or potential temperatures that we typically associate with the subtropical jet in a given month. And the blue bars are representing potential temperatures we typically associate with the polar jet. You may look at this and see how come you come up with two separate in December when there's only a single peak here within this distribution. Well, what we do is we take only the grid points south of 40 degrees north, thinking of these grid points as ones that are typically going to be associated climatologically with the subtropical jet. It's not going to be perfect. There's going to be some situations where the polar jet moves south of 40 north. But we use the distribution constructed from just these grid points in terms of the potential temperature that exhibits the maximum wind speed within each grid column to identify a frequency distribution of potential temperatures that are typically associated with the subtropical jet. And then we choose a half standard deviation away from the Gaussian fit to this distribution to denote the layer we use for the subtropical jet. For the polar jet, we use grid points north of 40 degrees. And here, when you look at the distribution, it actually ends up bimodal. Part of this is due to extrusions of the subtropical jet farther poleward, north of 40 degrees north, especially the higher potential temperatures. But it also is likely reflecting the potential temperatures associated with the polar night jet within the lower stratosphere. We're really interested in the Gaussian fit to this main peak at lower potential temperatures as being associated with the polar jet. And similarly, we pick a half standard deviation on either side of the peak of this Gaussian fitted to this distribution to figure out the isentropic layer we typically associate with the polar jet. So this is going to vary by each month, so the identification is specific to the month of the cool season that you're considering. For a superposition, what we're really interested in is instead of that double two-step tropopause structure, we want to look for the vertical alignment of those two tropopause break regions. And so as a result, we have that single-step structure. We can apply the same scheme we used to identify the polar and subtropical jets, but instead, we want to identify grid columns that feature characteristics of both polar and subtropical jets to denote that steep tropopause wall that's present in those particular cases. Then after this, to really retain jet superposition events that are more synoptic in terms of their length, in terms of the jet axis that's actually characterized by a superposition for our analyses, we filter these time steps to make sure that we're retaining those jet streaks where you have a string of jet superpositions along a considerable length of the jet axis. And so this is making sure that the events that are going into our climatology and our analysis aren't events that are just featuring one spurious grid point that might be identified as superposed. We're looking for these really synoptic scale length features that exhibit this steep tropopause wall type structure. When you apply this jet identification scheme in real time, you get plots that look like this. So these are for a couple of events here from December and April, just to highlight sort of the applicability of the scheme across the cool season. Where you see blue grid points, this is representing where the scheme identifies characteristics of a polar jet axis in terms of that PV structure and within the given isentropic layers that house each jet. Where you see green, that's where you're identifying subtropical jet characteristics. And then the purple shading here is identifying those grid points where we're identifying that steep vertical tropopause wall type structure. And this also gives you a sense of the types of events we're really interested in too, from a synoptic perspective, where you'll notice a string of grid points all along the jet axis here for both the December and the 2008 case. And I really should have put a QR code up here. My students are probably going to give me flack for this, for just putting the entire long string URL, because that's probably not the best choice. But Clary in our group did a really great job of applying the scheme in real time to GEF's forecasts, and she's got real-time forecasts that we're using as part of our NASA campaign that we're applying this in real time for. Now that we've identified these jet superpositions, we can look a little bit more at their impacts, their characteristics. So shown here is the frequency distribution of where we typically see these superposed jets over North America. And you'll see sort of a frequency maxima here off the West Coast, and then a primary maxima that is really situated over the southeastern US and along the mid-Atlantic coast here, right near the entrance region of the climatological North Atlantic jet. When we look at the times of the year that are typically associated with these superpositions, they tend to be most common during the shoulder season. So November and December reign supreme. You see a dip as you head into January and February, and then a rebound as we head into April and May in terms of a greater frequency once again as we exit the heart of the winter season. In terms of impacts, we've done some work associating these jet superpositions both with the occurrence of strong surface cyclones and atmospheric rivers as potential synoptic scale features that are conducive to inducing high impact weather in the vicinity of these superposed jet structures. So starting with the plot on the left, shown at the top here is just the frequency distribution of all cold season cyclones over North America, and highlighting the typical mean sea level pressure anomaly associated with those cyclones. And then on the bottom here, this is the frequency distribution of any cyclone that's within 1,000 kilometers of a jet superposition, just to highlight the difference in this typical intensity of these cyclones that accompany these superposed jet-like features. And just looking at the differences here between the medians, you can get a sense of these jet superpositions being associated with stronger surface cyclones that feature a mean sea level pressure that's about 0.7 standard deviation stronger compared to the full collection of all North American cyclones that you might experience during the cool season. And then shown here to the bottom left, this is showing where those surface cyclones tend to be located relative to the centroid of that particular jet superposition. So we take all those grid points that are characterized by a superposed jet, average their latitude and longitude together, and come up with a centroid for each individual event. And then we look in the XY space of where those cyclones are located relative to that jet superposition centroid. So the main thing that you want to take away from this particular plot is you'll notice a pretty decent clustering of these cyclones here in the upper right of this plot. This is consistent with what you'd expect from synoptic dynamic theory, that the left exit region is going to be a favorable spot for surface cyclogenesis. And sure enough, the cyclones that develop in this area also tend to be stronger than what we see in any other quadrant. Some of the variability you see in cyclones, either within sort of the southeast of the jet superposition centroid or to the northwest, might be a result of the different configurations of these jet superpositions. So we don't normalize to the jet axis here in this analysis. And so if you have a more northwesterly oriented jet, a jet superposition may be associated with a cyclone down here. It's still going to be in the left exit region through this particular analysis. But overall, for most of these superpositions, which tend to on average be west to east oriented, you see this pretty strong relationship here with the left exit region as favoring the development of these features. And then if we look at atmospheric rivers, we tend to find, if this yellow dot here is representing the average position of one of these jet superposition centroids over North America, the heat map here is showing the fraction of times at which you have a jet superposition where you exhibit also an atmospheric river at a location relative to that jet superposition centroid. And so overall, again, if you imagine that surface low pressure system tends to develop within the left exit region, this is a pretty favorable setup then for advection of moisture from the south in an atmospheric river type feature. So the existence of these atmospheric rivers downstream of the jet superposition centroid is definitely consistent with what we're seeing in terms of where we typically see those cyclones develop and then their impacts on circulation and moisture advection. Overall, we find that depending on the AR identification scheme that you use, that as many as 84% of jet superpositions are accompanied by an atmospheric river at some point in their lifespan. And again, we typically see those atmospheric rivers occurring beneath that jet exit region. So from these two past plots, you get a sense of how these jet superpositions can lead to really strong surface cyclones. You can get a sense then of how they're related to maybe a thermodynamic environment that's favorable for extreme precipitation through the presence of an atmospheric river. And shown here are just a couple of plots that highlight where you typically tend to see extreme precipitation here on the left and extreme winds within a subset of jet superpositions that are associated with really strong surface cyclones as well as an atmospheric river. And so what you see here from this particular plot is that at the terminus of that atmospheric river and in the vicinity of that surface cyclone that's developing, you tend to have a large number of events that are associated with precipitation that's exceeding the 95th percentile of the ERA5 climatology at those points for a fair number of jet superposition events. And then off to the right here, we look at how often during that subset of jet superposition events do you experience 10-meter wind speeds that are ranking above the 95th percentile over a large spatial area. And so you'll get a sense of the strong pressure gradient that's induced by those surface cyclones beneath the left exit region are producing strong winds on their southern and southeastern flanks once those cyclones develop. In total, we find that close to 2/3 of jet superpositions are accompanied by either the widespread occurrence of 10-meter wind speeds or 24-hour precipitation that can exceed the 95th percentile relative to climatology over a synoptic scale region. So you tend to see these environments manifesting in extremes with a pretty decent frequency once you are able to get these systems to develop. So now that we've covered some of the characteristics of how we identify these events and their impacts, let's talk a little bit more about their development in terms of how these structures tend to form. And conceptually, you can think of this process as beginning with the formation of a cyclonic potential vorticity anomaly at high latitudes with a polar jet streak on the equatorward flank of that cyclonic PV anomaly. And this can include features like coherent tropopause disturbances. Think of a vorticity max located poleward of the jet stream at higher latitudes. These features have also been referred to more recently as tropopause polar vortices. And the export of these towards mid-latitudes, as previous literature has shown, is really conducive dynamically to mid-latitude cyclogenesis. If you imagine what a cross-section through one of these PV anomalies looks like, shown here to the upper left, is a distribution of temperature anomalies with the 2 PVU contour highlighting the structure of the tropopause. You tend to have a dome of cold air beneath these cyclonic PV anomalies, and their export can also be associated with cold air outbreaks. And then you have anomalously warm temperatures in the lower stratosphere. You have the anomalously strong cyclonic circulation, so this is representing wind either into or out of the page in the vicinity of these cyclonic PV anomalies. You have a local maximum in potential vorticity as well in the bottom left. And then also, interestingly, for their development and formation, shown here to the bottom right, is the distribution of, this is going to be relative humidity anomalies in the vicinity of these tropopause polar vortices or cyclonic PV anomalies. And you tend to have anomalously dry air in the lower stratosphere, moist air in the upper troposphere. And this water vapor gradient can play an important role in differences in radiative heating gradients vertically. And that's one of the primary factors that helps to intensify these mechanisms as they meander at high latitudes in the Arctic. If we think about the subtropical jet side of things, we can have tropical anticyclonic PV anomalies, and these are generally associated with a subtropical jet on their poleward flank. These tend to be associated with weak upper tropospheric static stability, so they tend to favor thermodynamic environments that are conducive to vertical motions when you superpose them with one of these cyclonic PV anomalies at mid-latitudes. And they tend to form either through diabatic heating processes, through strong latent heating, convection, things of those nature, or also just the transport of tropical low PV upper tropospheric air towards mid-latitudes through Rossby wave breaking and other types of processes that allow for the export of that tropical upper tropospheric air towards mid-latitudes. You then need some sort of background confluent flow pattern, which allows these PV anomalies to find themselves into close proximity to one another. In the space between, you can get a rapid acceleration of jet wind speeds, consistent with what I discussed earlier as one of the hallmarks of these jet superpositions is being associated with strong upper tropospheric wind speeds. But what we were really curious about was what is the relative importance and role of these different PV anomalies on either side of the jet in driving the development of these superpositions. And so that's where we're going to go for the next 15 minutes or so. So conceptually, you can think about the process of superposition as just a material deformation of the tropopause structure at its most core level. So you want to go from this 2-step structure shown here to the single-step structure shown on the right. And then each of these arrows is colored according to a different process that can act to move around that tropopause structure to create that single tropopause break that you see there. So when we're talking about those cyclonic PV anomalies, as they move towards lower latitudes, that's akin to this polar tropopause break region moving from left to right within this cross-section, and you can conceivably think about that as a scenario through which this break region can be superposed with the one associated with the subtropical jet. We've done some preliminary work looking at where those cyclonic PV anomalies tend to come from. And so this is work that my student Eleanor Salm has been doing, trying to understand the origin stories of these cyclonic PV anomalies. And we find that typically when you look at where the tropopause polar vortices tend to come from, the blue shading is showing where the TPVs are early in their life cycle before they merge with the jet. And then the dark red colors are highlighting where those cyclonic PV anomalies are at the time they're making their closest approach to the jet structure. And so you can get a sense that they tend to merge with the jet most prominently over the Gulf of Alaska and over portions of southeastern Canada and the Labrador Sea region, but they tend to originate at higher latitudes, say over the Arctic Ocean, the high latitude portions of continental Canada, and even in some cases as far west as Siberia and the Bering Strait. We also take a look at how those cyclonic PV anomalies change their intensity as they move into close proximity with a jet superposition. So each of these dots is showing the relative position of one of these tropopause polar vortices in the time period leading up to their closest approach with a superposition, which is denoted by this particular dot here, is when the PV anomaly is within its closest proximity to the jet. And the color shading here is representing the intensity of that particular tropopause polar vortex in potential temperature space. So the larger the number, the larger the difference between the potential temperature at the center of that TPV, where it dips down to very low altitudes or cold potential temperatures, and the surrounding environment on the outside of that TPV. And interestingly, you'll notice that TPV strengthened for a period of time before it merges with the jet, likely through some of those radiative heating type processes that I alluded to earlier. But there's also continued strengthening after these features merge with the jet, which suggests a symbiotic feedback between the jet circulation, its internal dynamics, and how it's deforming the structure of that cyclonic PV anomaly after it's merged with the jet. We can also, if we go back to this sort of cross-section here, you'll notice that a key component that can also deform the tropopause is the presence of vertical motion within the upper troposphere. You can imagine this black line dragging down the tropopause. That can be a way to eliminate this intermediate tropopause step. You can also have strong vertical motions here equatorward of the subtropical jet, and the divergent outflow associated with that can further deform the tropopause at the altitude of the subtropical jet. So one of the analyses we did as well is try to understand or use the PV anomalies themselves to try and understand their respective roles in driving this vertical motion distribution in the vicinity of these superposed jets. So shown here is an example of how we do this partition. Basically, we take all positive QG or quasi-geostrophic potential vorticity anomalies poleward of the jet superposition centroid and group that into one isolated category. We do the same for the anticyclonic PV anomalies equatorward of the subtropical jet. And then we also group together any PV anomalies that are far remote from the superposed jet itself to highlight sort of the background large-scale environment in which these anomalies come together. We also consider, even though it's not shown, the role of lower tropospheric QG PV anomalies, such as those associated with positive and negative temperature perturbations near the surface that are induced by surface low and high pressure systems, and how they then feed back on the tropopause structure via their associated circulations. So we do this by using the equation for QG PV perturbation shown here. We can solve for a perturbation geopotential, which allows us to get a perturbation geostrophic wind that's associated with that subset of the PV. We plug that into our equation for the Q vector in the QG omega equation, and then use that to solve the QG omega equation to get the vertical motion that's induced by the circulations associated with each of these PV anomalies. And so shown here is a really noisy diagram, and I don't want you to focus too much on the relative magnitudes of anything, but wherever you see solid contours, that's representing downward motion. Wherever you see dashed contours, that's upward motion. And the color shading is representing the typical subset of PV associated with that vertical motion, or the type of PV anomaly that's inducing that vertical motion via its circulation. And the key takeaway here is you see a lot more blue here in the vicinity of the superposed jet compared to any other subset of PV, which suggests that a lot of the vertical motion that's being driven within that near jet environment once you produce a superposed jet is really accomplished by those polar cyclonic PV anomalies that are diving down from high latitudes. And those are having a predominant role then on restructuring the tropopause overall. I should also mention the important role of what's happening equatorward of the subtropical jet. And so here you can have strong ascent. That strong ascent is occurring within a really moist environment that can lead to latent heating and subsequent erosion of upper tropospheric PV. And so shown here to the right in the shading is the magnitude of the composite of diabatic heating that you can see during these jet superposition events, and it's overlaid with vertical ascent here in the black contours to give you a sense that diabatic heating is co-occurring with areas of ascent in the vicinity of a developing jet superposition. The blue contour is roughly the position of the polar jet in this composite, and the red contour is for the subtropical jet. But you can kind of get a sense that this area of diabatic heating is really occurring in the space between the two PV, two tropopause break regions, and it's also occurring predominantly equatorward of the subtropical jet. So you can think of this as acting to decrease upper tropospheric PV, erode that intermediate tropopause step, and allow for the development of that single step tropopause structure. We analyze the role of diabatic heating as a function of jet intensity as well. And what we find is that there's a ton of spread in the magnitude of diabatic heating in the vicinity of these extremely strong jet type structures. But what you will notice is that over the time leading up to sort of the jet's most intense time and afterwards, that you tend to have stronger diabatic heating on average with the most intense jets. So as you're scaling up the intensity of the jet, you're likely activating a more substantial diabatic piece on the equatorward side of that jet as an important formation mechanism, even though there is really substantial variability there compared to what you're seeing. Just to highlight this as well, as part of that study looking at the role of diabatic heating, we ran a couple of WRF simulations with full physics here on the left of a strong superposition that developed over southeastern Canada in 2013. Shown here to the right is what happens to the jet structure when you remove latent heating. And the first thing that jumps out is you'll notice a much weaker cyclone here within the left entrance region. As a result, there's weaker moisture transport in towards the northeast, and also at a dramatically less intense jet streak compared to the dry simulation. Where you really see differences in the tropopause structure, though, is in the upper troposphere. So shown here to the left is the tropopause structure in red from the full physics simulation, and you can get a sense of that steep tropopause wall that forms. And then on the in the blue contour, that's the structure of the tropopause from the no latent heating simulation. So they're pretty identical within the lower to mid troposphere, but where you see a big difference is in the role of that diabatic heating that would help to advect that tropopause break farther poleward via the divergent outflow associated with that convection. To talk a little bit more then about that influence of irritational outflow, when you have that strong vertical ascent that can lead to latent heating, that intensifies the upper tropospheric irritational wind. And shown here in green is where you're getting strong negative PV advection that's helping to drive that subtropical tropopause break poleward, helping to produce that steep tropopause wall type structure. And then on the bottom here, this is PV frontogenesis, so where you're acting via the wind to strengthen that PV gradient and induce an acceleration of wind speeds in the vicinity of those areas of strong diabatic heating and outflow. The last thing I'll mention here in terms of the role of these diabatic processes is we find that The restructuring of the tropopause is not just driven by the irrotational wind, but also just the balanced dynamical response to negative PV anomalies within the upper troposphere. So you'll notice that what's driving negative PV advection, that poleward extrusion of the tropopause break, is the balanced clockwise circulation associated with a negative PV anomaly equatorward of the jet, but then also that divergent outflow. And they can tend to play very similar roles here in the jet dynamics that are helping to accelerate what's going on. So this really suggests that in terms of modeling or characterizing these features, you not only need to get the immediate response of convection correct in terms of the divergent flow, but also the balanced response to that convection in terms of the negative PV anomaly that's produced, as that helps to maintain and keep the structure of the jet and its intensity moving forward with time. And so in the last couple of minutes here, I want to talk a little bit about future changes, thinking about what might happen in a future climate with these jet superpositions, once we've done a really good job here of highlighting their connection to high impact weather, how they develop, what the pieces are to their development. And so I highlight here in a warmer climate, you're likely going to be dealing with a more moist environment, and thus diabatic heating may play a more important role in the formation of these features within a future warmer climate. And then Alex here at NCAR did a really great job studying sort of the interactions between these negative potential vorticity regions that are synoptic scale in size and their interaction with strong jet streaks. And granted, we didn't notice a statistical relationship here that was significant, but there still is a positive trend in some of these synoptic scale negative PV areas interacting with the jet stream. And also a trend in the area of these negative PV regions with time, suggesting that maybe in this area where you're seeing a high frequency of superpositions, you might have more of a diabatic influence there that could be conducive to their development. There's also been studies that have highlighted differences in the movement or the character of the polar and subtropical jets. So on the bottom here is a study that shows across 5 different reanalyses how the separation between the polar and subtropical jet are changing across the reanalysis period of record. Granted, they use a different criteria for the polar and subtropical jet, but there's some suggestion that they may be getting closer together over North America and farther apart over the North Atlantic. That could have different impacts on the probability of superposition. And then shown to the right here is some diagnostics that John Martin has done on the separate polar and subtropical jet, showing how much those individual jets are departing from their equivalent latitude on average over a given year. The larger the number, you could think of that as the wavier of the structure of the jet with time. And so you'll notice positive trends here for both. And if you have, let's say, a wavier jet structure, that might be conducive to greater opportunities for those two jets to phase and become superposed. And so what we've done as part of this analysis here, and what our goal was to try and understand if we apply the same jet identification scheme to CESM simulations under different climate forcing scenarios, how might the occurrence of these jet superpositions change? And just to briefly cover some of this work that Clary has done as part of her dissertation, this is really focusing on the change in the frequency of jet superpositions by the end of the 21st century. Interestingly, in CESM, we notice a decrease in many of the locations that are characterized by a frequency maxima in the current day of jet superpositions. But we also see a greater frequency here at lower latitudes, both over the North Pacific and also along the Gulf Coast region, which is somewhat interesting. We also find that the environments that tend to accompany these jet superpositions tend to be more potent when it comes to, let's say, the potential to induce high impact weather compared to the historical climate. So I should mention, for this analysis here, where we're taking the difference between PV anomalies and wind speeds on the top relative to between the future climate and the historical climate, that we're evaluating these anomalies relative to each climate base period. So what we're looking at is how anomalous are the PV values, the moisture and stream function on the bottom, relative to what the base climate for that particular 35-year time period. And so what we see on the top is you have stronger positive PV anomalies poleward of the jet, slightly stronger negative PV anomalies southwest of the jet, which is somewhat interesting. And then in the shading, stronger wind speeds in the future as well. So you tend to see an increase in the magnitude of the wind speeds in association with these jet superpositions, which matches some of the work that Tiffany Shaw and her group has done at University of Chicago, showing that there's a likelihood for some of the strongest jet wind speeds to get stronger in a future climate when you're talking about wind speeds in the top few percentiles, which is where we tend to see these jet superpositions residing. And then on the bottom here, shown here in the dash contours, is the stream function anomaly associated with the future climate representation of the flow in the lower troposphere. So this is right around 1,000 hectopascals. And then the shading is representing the difference in the moisture anomalies associated with these jet superpositions compared to the historical climate. And so what we find is that the moisture within the warm sector of these surface cyclones tends to be amplified more relative to climatology than what we have in the historical climate. So there's a little bit more of an amplified thermodynamic environment that's accompanying these jet superpositions. And so we're in the process of just continuing to analyze some of this data here from CESM, tying it a bit more to near surface impacts, but preliminarily there's some interesting results here in terms of the resultant environments associated with these superpositions between the future and the historical climate. And just to close things out here, all of this serves as motivation for our NASA Fields campaign called NURTURE. The acronym refers to the North American Upstream Feature Resolving and Tropopause Uncertainty Reconnaissance Experiment. It's a mouthful there for sure. The whole goal of this campaign, though, is to try and understand precursor features prior to their merger with the jet stream and then the subsequent occurrence of extreme weather farther downstream. So we had a preliminary deployment this year with NASA's G3 with a more limited instrument payload. Next year, we're going to be able to use NASA's 777 that they just purchased and outfitted with a number of different instruments. So we're going to have all of these passive and remote sensors available to us for very prolonged flights through these cyclonic PV anomalies before they merge with the jet, trying to fly through some of these jet superpositions as they're developing and get a really Lagrangian sense of how these features are evolving with time by flying multiple days in a row. The whole goals of the campaign, I mentioned, it's really to understand what's happening to these features poleward of the jet stream where we have fewer observations. Can this then improve our jet stream predictability and downstream predictability of high impact weather? So one core focus is really trying to understand what is impacting the structure of these cyclonic PV anomalies as they're meandering on their own. How do they amplify the jet as they move then into close proximity to a jet stream and feed back then on the development of a very deep tropopause break type structure that's characteristic of a superposition. We're interested in the role of diabatic processes, both in terms of radiative heating anomalies in the vicinity of these cyclonic PV anomalies, the role of moist convection equatorward of the subtropical jet and how that feeds back on the tropopause structure. And then also as these tropopause features move over oceanic locations, there's considerable sensible and latent heat feedbacks that can then communicate with the middle and upper troposphere and either lead to the decay of those TPVs and thus the jet structure as well. If you're weakening the tropopause wall from below, for example, how does that then impact the downstream evolution of the jet overall? And how does the thermodynamic environment beneath those cyclonic PV anomalies evolve as they continue to move off towards the east? This past year too, NURTURE has sat in a really unique ecosystem where we had 3 ongoing simultaneous fields campaigns across the North Atlantic and across North America. We had AR Recon, which was flying in the North Pacific and in the Gulf in a couple of instances to sample features before they moved into our domain across portions of southeastern Canada. We were really focused on sort of this antecedent tropopause polar vortex-like structure, how it interacts with the jet stream. And then as those features move downstream, Nautic, which was a field campaign focused on extreme weather over Western Europe, the role of these dry intrusions in helping to drive the development of extreme weather and convection in the vicinity of frontal boundaries attendant to those surface cyclones. They could take the observations we had, hand it off to them, and then get a full sampling of these features as they navigate all the way across the basin. So just to conclude here, I hope I've convinced you over the last 50 minutes that these superpositions are an environment that is conducive to extreme weather when they develop. It doesn't always happen, but there's a pretty strong relationship there between a variety of high-impact weather events during the cool season. The development is really strongly modulated by this unique interplay between these polar cyclonic PV anomalies, their internal dynamics, and how they interact with a lot of these moist diabatic processes equatorward of the jet. We find looking in the future that jet superpositions are less frequent in CESM. It remains to be seen whether we'll get similar results with other climate models, but we do see a more potent dynamical and thermodynamic environment when these superpositions do develop. And then we have all of this as motivation for our field campaign coming up or continuing next year, where we hope to get some of these observations of the jet superposition process in unprecedented detail. As everything here is reliant on what we're seeing from model data, from reanalysis. And so it'll be great to pair it with actual observations of these structures in greater detail. So with that, thanks again to Chris for the invite. Thanks all of you for coming today, and I'm happy to take any questions.
Thank you. Very great talk. It's always a treat, at least on the RAL side for sure, to have synoptic meteorology and dynamics talks. So we'll have probably a lot of good questions. We have about 5 minutes. I will remind people online to please type in their question on the Slido, and then people in room, we have questions here.
Yeah, I'll echo the comment about synoptic meteorology. This is a course I taught in my former academic life. So very heartened to see some of the plots that you showed. Remind me of when I taught the class. 2 questions. One, about your metric for the merging. And one thing I would want to know is, what about tropopause folding? Could you get an explicit metric for that you might include in your identification methodology? And then second is, a lot of your method goes to like these thresholding criteria, and have you thought about maybe automating that a little bit with use of AI/ML?
Yeah, no, great questions. So getting back to the first question about the tropopause fold type metric, it's a really interesting one too when it comes to thinking about if there's a way to quantify the existence of that type of feature. We've talked about it, or in the past, we haven't developed it, but coming up with some metric to look at sort of the depth of that tropopause break region, that would certainly be a way to sort of get at that folding structure. I think there's ways we could, be creative with the way that we're applying the identification scheme to look at how maybe the upper level PV wall is displaced relative to the folding region underneath, because you can sometimes get that. If you imagine launching a weather balloon, it's going to cross through the high PV region and back into the free troposphere. And so I think there's ways we could get at it through the algorithm that we have currently. Regarding the AI/ML type sort of perspective, that's certainly something Clary and I have talked about of a future sort of application, is whether we can take the observations we have as a training data set that we can then apply and have it work more efficiently, say, with a greater number of models, for example, longer time periods, a more global perspective perhaps. But I think that the approach that we've used with some of the more empirical thresholds could serve as a perfect training data set for that particular activity. Yeah.
And one more comment, and then I have to go, is think about for the the tropopause folding question, we're developing a lot more high-resolution model data sets, like at convective permitting scales. And I'm wondering, maybe look at those to see if you can get the folding.
Yeah, no, that's a great suggestion. Absolutely. Yeah, because some of our precursor or preliminary nurture data, these are really, really sharp folded features when we have some of the observations to go with it. Yeah. Thanks so much, Chris. Yeah.
This is a question from a marginal synoptician, so it may be silly, but is there ever a jet superposition between a cyclonic anomaly and the subtropical jet and the polar vortex features?
Yeah, you mean in terms of like a more Arctic jet, polar jet type superposition?
Well, no, the polar jet and then the subtropical, cyclonic wave in the subtropical jet.
No, that's a great question. I think that usually that type of scenario, it tends to show up in some of those superpositions that tend to be more associated with severe weather outbreaks over the eastern U.S., where you tend to have maybe a short wave that's moving across the northern Rockies and a cutoff low that's going across the southwest.
Yeah, for instance. Yeah.
And so that type of scenario is definitely one where you have some precursor set of cyclonic anomalies along both jets that downstream help to facilitate it. So yeah, that's definitely a nuance to this, is that you can have these cyclonic anomalies play roles along both waveguides. Yeah, and that is hidden, I think, from the conceptual approach used here. Yeah,
well, obviously, it sounds like the anticyclonic, piece is more common for these superpositions. But yeah, I have personally seen those kinds of juxtapositions.
Yeah, absolutely, definitely. I think even this week, I haven't looked at Clary's stuff this week, if it's not, or I don't know. But I would think the setup that's ongoing right now with the severe weather in the Central Plains is kind of the one I would think of as one of those scenarios where we're likely seeing maybe a superposed jet that's developing off the northern Great Lakes from the outflow of the convection that's been occurring the last couple of days. Yeah.
Hey, nice talk. I really enjoyed it. It was mostly on the weather time scale, which is very fascinating. And my question is about comes from this third point. Projected to become less frequent in CESM. So, do we have a sense of what might make a season a conducive year for a lot of these superposition events, for example, in the North Atlantic?
Yeah. No, the question about intraannual variability and interannual variability as a modulator of superposition activity is a totally open question. My gut feeling is it'd be really interesting to go back and look at years with high frequencies of superpositions in a given location, and what the relationship is to any sort of upstream precursor, say in terms of maybe a relationship with ENSO, MJO activity, things like that. I will say that in terms of a favorable environment, it tends to occur most often in situations where you're able to amplify a Rossby wave along one of the two waveguides, so that you're able to allow for those excursions far enough to permit the merger of the two. So I think anything from tropical cyclone, recurving tropical cyclones, all the way through long-term modes of variability could all be factors that drive things there on those longer timescales. Totally open area of research, though, that'd be interesting to look at.
Yeah, and maybe just one quick follow-up. Thanks. It makes me curious too, because it's interesting to think if you're getting a signal from external forcing, right? Are these mechanisms similar on seasonal or interannual timescales that we're seeing on these long climate timescales? But I'm just curious about that. That's more of a comment than a question, but curious. Yeah, I'm interested to see where this comes.
Yeah. No, I totally agree.
All right, I'm sad that we have run out of time for formal questions, but do feel free to stick around here. And obviously, Andrew works here in town, so hopefully we can have him back or have collaborations ongoing between the two places. So let's thank Andrew again for coming out today to present a very exciting research topic.